Okay, so in the last lecture, we saw the necessity of um, interpreting stochastic integrals. You remember that we had to go back to the Riemann sums, and depending on the choice of this point, which is a point in the interval when we have a partition and we integrate to approximate the integral by a sum, the result depends on the choice of the point inside the integral, which is something that doesn't occur in the normal integrable functions in the Riemann-Stieltjes theory of integrals or definition of integrals. So we did this example of w dw, this integral, and we saw that in the Ito interpretation, the result, we just calculated the average, but we saw that the result is 0, whereas in the Stratonovich interpretation, because of the fact that we choose this as the middle point, there is a remaining correlation, and then the result is uh, different from 0. You remember we did this calculation, so we had this result that the average of the Stratonovich is sigma squared divided by 2 and times multiplied by tau. And then we tried the standard procedure to calculate an integral such as this one here. So x dx is dx squared divided by 2, w dw should be, or the standard calculus tells us that it is w squared divided by 2, the integral. So between 2 and 0, this gave us wt squared divided by 2, and once we average this result, we get the same result as in the Stratonovich case. So what we found is that Stratonovich is okay, is compatible with the standard calculus, but Ito, the Ito interpretation, the Ito integral is not compatible with the standard calculus. So we could just give up and say, well, it doesn't make sense to continue with the Ito interpretation. But what Ito did actually was the opposite, was to really try to make sense of all this. And for that, we have to, or he had to find a new calculus, a new, really go to the basic rules of calculus. So this is what we are going to see now. So this is our fourth section, which is the Ito calculus. And to start, we have to ask ourselves why the Ito integral is not compatible. Why the standard calculus doesn't work? So, and the reason is the following: if you the standard calculus tells us that the x dx, or the w dw, is dw squared divided by 2. I write this question mark here to just to recall that in the Ito integral, this fails. Actually, this is not true. And we have to ask ourselves why this is not true, and we have to explore this. So the best way is to go back to the discrete case. So let's write the left-hand side in the discrete version of the left-hand side. dw is just the increment of w, so it's w evaluated at t plus delta t minus w evaluated at t. And this should be equal to dwt squared, which is wt delta t squared minus wt delta t. Okay, and again, this in the standard calculus, this we will now check what means to be equal to. And to do it, let's of course these two quantities are not equal in the finite case, So let's try to calculate the difference between these two quantities. What I will do is to write this, the left-hand side, as the right-hand side plus something. And if you do a little bit of algebra, this is the result. Let me write the result, and I will explain term by term why it is equal. This is the left-hand side of the equation. And why it is so? Well, you can see that you have just to sum and subtract the appropriate terms. But check that the same terms here are there. Wt plus delta t square cancels with this one. No, if we expand this square, so we get minus 1/2 Wt plus delta t square. So this cancels with this. On the other hand, Wt squared, this is a minus, and with this minus, we get a minus Wt squared, which is this one here, Wt multiplied by Wt. So, and finally, there is a 2 Wt plus delta t Wt with minus, but this minus is plus, and the 2 cancels with this 2, so we get this term. So this term is identical to the left-hand side of this equation. And you see that the right-hand side is here. So this Wt plus delta t minus Wt is the difference between these two terms. So what happens in standard calculus? Well, we have an increment. This is dw, let's say, Wt plus delta t minus Wt square. So this is for the delta t square if w were an analytical function, a function with a finite derivative. So this should be of order delta t square. But what happens with the Wiener process? The Wiener process, we saw that it has some, although it is continuous, but the derivative is not well defined. And in fact, there is a very a property that we already know very well, which is that the space, remember the Wt plus delta t minus Wt, which is the motion of the Brownian particle, the dispersion is of order delta t. So this increment squared is of order delta t. And that's the whole story. So something that for a normal function, for a function with finite derivative, this is delta t squared. This should be delta t squared. And then delta t squared is negligible when we integrate, because the number of terms in the integral is 1 over delta t. So this question mark tells us that this is equal to this up to first order in delta t. But the problem with the it interpretation is that this is no longer of order delta t. This is of order delta t square. So this is square. So the square is of order delta t. So we cannot neglect this term. This term cannot be neglected. This first order is kind of the key point of the whole theory of stochastic differential, or the whole theory of Ito calculus. So we cannot neglect this. So the Ito calculus consists of keeping this term. So we have to keep this term, which is 1/2 dw square. So this means that we have to put it here. Okay, and this will, because this term is of the same order as the other terms, as dw, as the terms of order delta t. So this is the problem. So now let's interpret this one. This is what Ito did. Of course, we here in this course we will not give you a complete proof, but the idea is that this is a stochastic in principle. No, this is but the idea is that the only relevant term here is delta t, and this is deterministic. So this is in fact sigma squared delta t dt. Okay. And this is the whole story of Ito calculus. Ito calculus is just to keep terms of order dw square, and then whenever dw square appears, replace it by sigma squared dt. Let me write it here. This is the recipe for the Ito calculus. Keep terms of order dw and replace this by sigma squared delta t dt. This is kind of a heuristic recipe that But what Ito did was to prove a more precise result, which is called the Ito's lemma. Let me erase here. And Ito's lemma is just the application of this recipe to one of the basic problems in calculus, which is the chain rule, or if you prefer, because we are talking about stochastic differential equations, is going to be the change of variable in a stochastic differential equation. So if we have a stochastic differential equation written in this form, dx f dt g dw, interpreted as Ito. And now we want to change the variable. We define another variable, which is y. So we have y, which is y of x as a function of. So if x is the solution of this equation, we want to find the equation that obeys y. This is the change of variable. And usually, what do you do for a change of variable? Well, we want to find the equation. So usually in standard calculus, we will do like that, the chain rule. So we derive y with respect to x, and then we multiply by dx, and dx is this one, so we get the equation. But now we know that we have to keep terms of order dw, and dw is here. We have to keep terms of order for the dx squared. So we have to go farther in the Taylor expansion and do like that. And now we replace dx by its value. So dx is f dt g dw. And here we have to do the same. We'll do it in a very abbreviated form. So we have to do the same. And this is a square, sorry. This is a square. Okay. But now analyze this term. This is we have the square of the first term, f squared dt squared, but this is dt squared, so this is, we don't care about, we only have to keep these terms, dw squared. Then there is 2fg dt dw, which also vanishes. This is, as I said, we cannot present here a rigorous proof, but you can imagine that it is the only term that has problematic, that it is problematic, as we have seen, is dw squared. So here we only retain g squared dw squared, this one. Okay. And now let's apply the second part of the recipe. We replace dw by sigma squared dt. So we can now erase here and do like that. So this is Ito's lemma. Let me write it now in a more just graphic. I will group the deterministic terms and the stochastic term. Okay? So you have here f I prime, y prime here is the derivative of y with respect to x. So and we have y second derivative, which is this term. And this term is the new one, let's say, with respect to standard calculus. The other two, this one is the one that we got with the naive, just with the first part, no? Which is the not naive, but the standard calculus. And this is the extra term. This is why this is called Ito term. And it's a term that appears because of this Ito calculus completely. It's something that will not appear if we change variable using the standard calculus. Okay, let's look at this in an example. So the example will be the equation that we wrote at the beginning of the lesson, x dot minus alpha plus xi. Since we are used to this notation where the equations are f plus g times the noise, here f will be minus alpha x and g will be minus x. Okay. And the noise, as always, is a Gaussian noise, white noise, with the dispersion, quadratic dispersion sigma square. Okay, so when we imagine the equation, the deterministic equation, we know perfectly that this equation, the x dot minus alpha x, the solution is the exponential. But why we know that it is exponential? Actually, what we are doing implicitly whenever we solve this equation is the following. Let me do it here. We take this equation and then we divide by x. So this is what we do actually. And then here you immediately recognize the derivative of the log. So this is the derivative of the log. Then we can integrate this and we get log of x equal minus alpha t, and then we get x exponential. So what we are really doing when we do this procedure is to solve the equation for the new variable log of x. Actually, we are doing a change of variable. So let's try to repeat this using the Ito calculus. So the idea is to consider this new variable and change the variable here in this equation using this one. So we do it using, of course, Ito's lemma, because we interpret this equation is interpreted as Ito. So we have to do this. And then we first calculate the derivative of y with respect to x, this y prime that appeared in the lemma. Is of course 1 over x. So I have here, remember that the first term was x dot times the derivative, which is 1 over x, so x dot divided by x. So this is what what we have done before, no? In the when we did this change of variable, no? The variable of the log is the variable is x dot divided by x. This is a so very basic fact, no? The derivative of the log is of a function, the log of f is or the log of a function is the derivative of the function divided by x. But here we have the Ito's lemma. As I said before, the Ito's lemma essentially is the chain rule. So we have to add here the Ito term. So it is the second derivative. The second derivative of the log is 1 over x squared minus 1 over x squared. So you have to add here this one. Remember what is the Ito's term? Is sigma squared divided by 2. This second derivative of y with respect to x. So this one. And now g squared, but g is minus x. So we have x squared. And this is the equation. This is the equation for y. And of course, we have done. If the change of variable is not so, now you have to express x as a function of y, and it will be a mess. But here we have done this change of variable, knowing that the equation is going to simplify a lot. So now we replace x dot by the original equation, and then x divided by there is an x which cancels with this x, so we get only and here x also cancels, x squared cancels with x squared, so we get minus alpha minus sigma squared divided by 2. And then here in x dot there is also the noise, which but multiplied by x but cancels with this x, so we have minus the noise. So this is the equation for I, and this term is the Ito term, so it is due to Ito. So now we can integrate this equation. This is rather easy because there is no y here, so we can integrate this. This is minus alpha t, well, the initial condition, minus alpha t sigma squared t. So this is the integral of this part, of the deterministic part, and now we have the integral of the white noise. But the integral of the white noise is the Wiener process. So we have this. And now we go back to this is the Wiener process. Now we go back to the x, which is the process that we want to solve, and this is the exponential. And even though this is a bit strange, well, there are possibility. It's easy to analyze this. We could do a lot of things with this expression. It's in terms of WT. In the exercise, you will have also to solve this equation for many values of alpha and look at the bifurcation diagram and the stability of 0. Actually, the sigma squared divided by 2, the Ito term, you see that there is a minus here, so it makes the exponent more negative, and the exponent is how fast the system is relaxing. So this term is stabilizing zero. We will see this in now. Let's consider now the same equation, but interpreted as a Stratonovich. Okay, now we interpret it as Stratonovich, and of course the result is different. Now we can apply standard calculus, and standard calculus tells us that y is x dot divided by x, and then this is minus alpha minus the noise. And you see it's the same result as here, but without the Ito term. And now we solve this equation, we integrate as before, there is alpha t minus w, and then we have the exponent. And you see the difference between the two interpretations. In one, there is this term, and these terms, as I said before, makes the exponent more negative, no, in the Ito than in the Stratonovich. There is this sigma squared divided by 2. So Ito makes the zero more attractive. It's more stable. You will see this in the exercise when you study bifurcations based on this model. So this is a term that stabilizes zero. Okay, so we have seen the stochastic integrals, the necessity of Ito calculus, and then how it works, the Ito's lemma to solve stochastic differential equations. Now let's go to the next section is to put a little bit all this in order. So the title is stochastic differential equation. So, but I want to really make a kind of to compare the two interpretations and to see how they work in a stochastic differential equation. So as always, we deal with this type of equation, and as we have seen, these symbols, just like that, they don't mean anything, or they are not precise enough. You need to have you need to provide an interpretation. Usually, in some texts, you will see that the Stratonovich interpretation is indicated by this small circle. But this is not a standard notation. It was, some people use it, but it is always safer to just indicate explicitly in the text. If you write a paper with a stochastic differential equation, you should say in the text whether it is interpreted as Ito or as Stratonovich. Another notation, which is the one that the mathematicians prefer, is this one with differentials, and also you can use this little circle to indicate the Stratonovich interpretation. Yeah. But as I said, this is not completely universal notation. So let me comment things, because this is very surprising. No, you have a equation. First, you have to provide an interpretation. So some people say, what is the interpretation? And so there are some properties. Actually, the two interpretations are essentially, there are tools to work with the stochastic differential equation. So you can choose one of the other, and you can go from one to the other, and this is what we are going to see in this section. So let me first explain some features of the Ito and the Stratonovich interpretation, and why they are, these features are really what tell you which one you should use. But you can use the two at in the same problem, if we will see in a moment an example of that. Keeping always the coherence, let's say. So, okay, first, one of the main properties of Ito is this one, is that the product of the noise, that this product, x times the noise, or gx times the noise, or like that, this product is zero, and it is easy to see, because remember what Ito prescription is to, this is, we saw it in an integral, but you can see it here as well. X dw, what is dw? Well, dw is always is wt plus delta t minus wt. But what multiplies dw must be evaluated at the first point, at the beginning. So in this case, at wt. Okay. So now remember the main property of the Wiener process, that the increment is independent of wt, and not even independent of wt, it's independent of all the past. So this is the motion of the Brownian particle in an interval of duration delta t, and it doesn't depend on wt or on the past of the. For that, you need also the Markovian property. But essentially, this is these two guys are independent. So this and this, x of t, because x of t is a solution of differential equation, so it depends only on the past. So these are independent stochastic variables. And if they are independent, then I can factorize this, and the mean value of this is 0, as we have seen also in the mean properties of the. So for Ito, the product of x times the noise or x times the Wiener process is 0. And this is going to be very useful, because so in Stratonovich it's not that way. In Stratonovich, remember that this product, the prescription of this product is that x of t is in the middle of these two guys. So x of t is no longer, well, x of t is, this t is not t, is t plus delta t divided by 2. It's this time x is evaluated in the middle of these two times. So this is no 0. And actually, there are ways of calculating this product. There is something called the Novikov theorem, and but it involves a functional derivative, so it's more difficult. And in Ito, it's immediate that you can just neglect. You can, this is 0 for any x or any function of x. So this is very, very useful. We will use it in the following sections. The second point is that that if this function accompanying the noise is constant, well, you can see here, if we go from the differential equation to the integral, what we get here is the integral of dw. This is ft dt prime plus, and the integral of dw is just the Wiener process. So we get wt, and we don't get really an stochastic integral. We get a trivial stochastic integral, which is the integral of dw. So this means that the Ito and Stratonovich are equivalent. There is no need when this is also some of the confusion that Langevin equation and many equations in physics, the noise is like that. This is called additive noise, because the noise enters in the equation as you see, enters in the equation. This is constant, so it's plus noise. So this is additive noise, and for additive noise, you don't need to distinguish to provide an interpretation. This is why many books on non-equilibrium statistical physics, very elementary books, where they deal with Brownian motion and the Langevin equation, which is an stochastic differential equation, which we will see in detail in a moment. They don't talk about Ito, Stratonovich, and so on, but it is inside the whole theory. But if it is additive, you don't need any interpretation. And the last property, which is important, is the following: that you can imagine that the stochastic differential equation, one of these, you can imagine this equation with a color noise. With color noise, you don't need an interpretation. It's fine. There is because color noise is differentiable, and you can have color noise is fine. So if you don't need an interpretation, you can think of an equation with color noise, and then make the limit of the noise. We have seen before some examples, the Orsten-Uhlenbeck process, and some other examples where a color noise can go to a white noise. So one can ask, if I have my equation with color noise, and I make the correlation time going to 0, what is the result? Well, the result is the Stratonovich interpretation. if there is no any other small scale. So there is some. This is a very well-known result, but in the 80s there were some papers warning that if in your process, when you have more variables and so on, and you eliminate more variables at the same time as you do this limit sometimes does not commute with every other limit. So but in principle, if I have an equation like that with color noise and I make the limit tau going to zero, tau is the correlation time, then I get the Stratonovich. So one would say, Stratonovich should be the appropriate interpretation, and this is true in physics. If my equation comes from uh, in physics, you never have a real white noise, as we have said many times. So you have a color noise, but the scale of the correlation is so small. This tau is so small, you know, compared to the evolution of the system, that I can consider as a white noise. In this case, the Stratonovich interpretation is the appropriate one. So one could say, why Ito? So Ito is appropriate, for instance, when you have, for instance, in financial markets, when the price of the price of stock or asset tomorrow depends on the price yesterday plus some noise or plus some function of the noise. So for systems with discrete time, usually the interpretation, because you update, let's say, the process x of t with noise, but depending on x of t in the last step, when you have a discrete time and you make a continuous limit, then Ito should be should usually Ito is the one that you get. So if the we will see this tomorrow, but these are the three comments that I wanted to